Welcome back to elementary statistics. In this video, we're going to talk about Anova, the analysis of variance test. In some of the early hypothesis tests we've looked at, we were comparing the mean of one sample to a prediction, an estimate for a population, or comparing the mean of one sample to the mean of a second sample to determine if they were equal or not. The idea of Anova is going to expand that out to give us situations of more than two different samples that we want to compare. So the idea of an analysis of variance is to compare the mean of a collection of three or more samples. You'll see quickly that in the case of two samples, even though technically Anova could do the job, you would not want it to. And the process of analysis of variance is sometimes known as the F test because it's going to rely on the F distribution. And just like with all the other distributions we've talked about in this course, there is a table of critical values for the F distribution available. Although I want to point out that this is a dense table. There's a lot going on here. The first thing that I noticed the first time I saw the F table is right here above my head. This is the critical values table for F, specifically in the 95% alpha equals 0.05 confidence level. That is strange. Tables we've looked at in the past, we've had one table and we've been able to go column by column to change the level of alpha. We can't do that here. We have to go to a completely new table. In the columns, we are looking at the degrees of freedom for the numerator. In the rows, we are looking at the degrees of freedom for the denominator. That's a lot that's happening. All right, so this is the alpha table behind me or the F table for alpha is 0.05. There are other F tables for other values of alpha. There's no reason that you have to be stuck with alpha equals 0.05, but it's the one that I tend to use in my videos because it's probably the most common significance level that you see in hypothesis testing. All right, let's get back to the notes and start working through some of the theory here. There are a number of formulas that we're going to be looking at. The calculation for F is given as the variance between groups divided by the variance within groups. And that doesn't make any sense to you right now, and that's okay. We're going to build up to it. But I wanted to lead off with that along with some notation. Remember, variance, we didn't use very often in this course. Variance is the square of the standard deviation. So if we use S to represent standard deviation, then S squared is variance. Variance between is going to be S sub B squared. Variance within is going to be S sub W squared. There's our notation. When we're talking about ANOVA, the null hypothesis is always going to be some form of there is no evidence of a difference between the means in these samples, and the alternative hypothesis is going to be that there is some evidence of a difference between the means. And similar to some of the other tests that we've done, if our value of f is greater than the critical value, we will reject the null hypothesis and accept the alternative hypothesis. If f is less than the critical value, we will accept the null hypothesis. Right. Generally speaking, f equals the critical value is going to fall into the accept range as well, but equals almost never happens, and honestly, it's not worth worrying too much about. All right, so there is the idea, there's the theory, and now we have to get to the calculations. And there's a lot of notation going on here because we need so many different pieces of information. We need a collection of samples. The first thing we need to know is how many samples are there? That, again, that's not how many members are there in a sample. We are comparing several different samples. It could be as few as 3, it could be as many as 50. The first thing we need, why did I say 50 at the stop? It could go 50, it could go higher. The first thing we need to know is how many samples are we looking at. We're going to represent that using the letter K. Then we're going to number our samples. Sample 1, sample 2, down through to sample K. And for each sample, give myself a little bit more space here. For each sample, we're going to want the mean. We're going to want the standard deviation. And we're going to want the size. Right, so the mean of sample 1 is x bar 1. The standard deviation is S1. And the size, the number of elements in sample 1, is little n1. Little x bar 2, little s2, little n2. That didn't look like a 2. Let's make that look like a 2 over there. And then all the way down, eventually we'll get xk, sk, and nk is a bunch of variables, right? How many are there? I don't know. There's definitely more than 2 because if there were only 2, we would not be going through all of this. Now we need, all right, that is our input data. Finding x bar, s, and n in and of itself for a single sample was an entire problem earlier in the course. We have to do that several times before we can even get started at this point. So I think that goes pretty far to show this is not something we want to do if we can avoid it, but there are very often times that we can't avoid it. Anova is probably one of the most common statistical tests used in research. All right, but now that we have all of that data, we're going to start calculating some things. We are going to add up the sizes of each of the samples to get the grand total. How many members are there between all of the samples we are studying? We are going to get the grand mean, which I'm going to represent using a capital X to contrast it with the lowercase x's for all of the pieces. Sometimes you'll see somebody use a subscript of G on this to remind you that this is the grand mean, the mean of everything. And what we're going to do is literally, if we had all of the individual data, we would add up all of the scores from all of the samples and bring them all together. Since we don't want to do that, we're going to take this as a weighted mean. We're going to weight the mean of each group by the number of elements in that group, and we're going to divide by the sum of the number of elements in all of the groups. Or we could make things a little bit simpler. Sum of n times x bar all over the grand total, capital N. We've already calculated it. We can use it here. But I wanted to show you that first step to remind you that what we're doing here is taking a weighted average. There's nothing all that weird going on. Next, I want to take the within group variance, which is also going to be a weighted average. All right, so the within group variance is S sub W squared. And remember, the variance is the square of the standard deviation. So it shouldn't be surprising to you that I'm going to weight, well, I'm going to use a slightly strange weighting of n minus 1 times little s squared. Right? Although when you think about it, little n minus 1 makes sense. That is something that shows up in the standard deviation formula. So that's why we're using that as our weighting. And then we're going to divide by the sum of all of the n minus 1s. Interesting thing that happens in this. Again, this is a weighted average, and showing it to you as a weighted average, I think, helps understand where it's coming from, why we're doing it. But to make calculations easier, you might find that it's useful to realize that the sum of n minus 1 is big N minus k. So since we already know big N, since we already know k, using those might make this calculation a little bit faster, and it will help show off where some of the other things are coming from a little bit later. Finally, the between group variance, S sub B squared, is the sum of, here it gets really interesting, little n times the quantity, little x bar minus big X bar squared, all divided by k minus 1. This is not a formula that makes sense right away because we didn't really use it much early in the course, although we did see this formula or something close to it. This is the weighted standard deviation. Right? X minus x bar squared, add those all together, divide by n minus 1. Well, add them all together, sample minus mean, whole thing squared, divide by number of samples minus 1. We just have this extra weighting factor of little n on each of the terms. Other than that, this is the weighted standard deviation. We're calculating the standard deviation of all of the sample means within the group of samples. Sort of. Close enough. Slightly different formula, but the same idea, and kind of keeping that in mind, for me, helps me remember what's going on here. All right. Remember, getting ahead of myself, sorry about that. I'll get back to that in just a moment. But I want to remind us one more time that the calculation here, f, is SB squared divided by SW squared. So we have these things, we divide them, that's what we're looking at. In the numerator, we're looking at SB. And this K minus 1 that shows up right here, the numerator df, df for the numerator, or sometimes just dfn, is K minus 1. In the denominator, we're dealing with SW. And we have this NK right there. df for the denominator, depending on what your F distribution table looks like, this is the denominator's df, or sometimes just dfd to abbreviate it, is n minus k. That's a lot of calculation. There's a lot going on there. And I think that it's probably for the best to not worry too much about how do I make this make sense in context. I think context is relatively easy. We've done enough hypothesis testing at this point. Let's go to a pure numerical example, which is not something we often do in statistics, but I think it makes sense here. Let's not worry about where this stuff is coming from and just deal with what we have. All right, let's look at a situation where I have 3 samples. In the first sample, X bar is 15.5, S is 9.1, and N is 7. In the second sample, X bar is 4.0, S is 5.2, and N is 5. And in the third sample, X bar is 5.8, S is 5.9, and N is 6. I'm going to look for a 95% confidence level, which is the same thing as saying that alpha is 0.05, right? 100% minus the confidence level, turn it from a percent to a decimal, that's how you get alpha, which is good because I have the alpha equals 0.5 table for F. Again, there are tables for every value of alpha. Here's just the one that I'm working with. I also need to know big N in order to do work on this. 7 plus 5 plus 6, which is 18. And from that, I can calculate that df for the numerator is 3 minus 1, which is 2. And df for the denominator is 18 minus 3, which is 15. A lot of variables here. Again, remember that little n1, little n2, little n3 is the size of the individual samples. K is the number of samples, and big N is the total of the sizes of all of the samples. We can use those to find the degrees of freedom for the numerator and for the denominator separately. Let's pull up my F distribution. My degrees of freedom in the numerator was 2. My degrees of freedom in the denominator was 15. Bringing those rows together, I get to write here. Critical F is 3.682. Write that down so we have it available for reference. And then get on with the rest of the calculation because there's a lot of calculation in this process. I need my grand mean. X bar is the sum of n times little x bar divided by big N. There's only 3 samples in this situation, so instead of trying to set this up in a table, I'm just going to bring it in here. But I could set this up in a table and get my x bar, my n, and my n times x bar as entries. But again, just 3 samples, so let's just deal with it. I have 15.5 times 7. I have 4.0 times 5. And I have 5.8 times 6. My calculator is happy to do the work for me from here. And I get that the grand mean is about 9.1, 9.072, but I'll round it to the nearest tenth because that's how it will be useful for me in a little bit. All right, on to the next calculation. SW squared is the sum of n minus 1 times little s squared all over big N minus k. Again, if this was a larger collection, I might go to tables and have a column for n, n minus 1, s, s squared, n minus 1 times x, s squared, and then add them all together. But with just 3 samples going on here, I think setting it all up in situ is going to make sense. So for sample 1, n was 7, so n minus 1 is 6. S was 9.1, and we square it. For sample 2, n was 5, 5 minus 1 is 4. S was 5.2, and we square it. For sample 3, n was 6, so n minus 1 is 5, and S is 5.9. We're going to want to square that. In the denominator, we have big N, which is 18, minus K, which is 3. And let my calculator do the talking from here. I get that SW squared is 51.94. Next, we have to calculate the between group variance, SB squared, which is given as the sum of n times little x bar minus big X bar squared all over k minus 1. Once again, I could, if this was a larger sample, turn to a table to set up columns for X bar, big X bar, the difference, square it, multiply by n, and bring everything together. But since it's just 3 samples, I think we can get this done in the situation with the formula here. For the first group, n is 7, little x bar is 15.5, big X bar, just off the top of the page here, is 9.1, and we want to square that. Then we will have n2, which is 5, times mean of the second one, which was 4.0, minus grand mean, which is still 9.1, and we'll have 6, the size of the third group. Mean of the third group was 5.8, still subtracting 9.1, still squaring it, still dividing by, well, k is 3 in this case, minus 1. And let's let my calculator do the heavy lifting one more time. (241.055). I probably didn't need to write out that much detail, but I'm going to anyway. One last step. SW squared, the within group variance, goes in the denominator. SB squared, the between group variance, goes in the numerator. And we finish up by calculating here that F is 241.055 divided by 51.94. And that comes out at 4.641. It's been a while since I wrote it down, but if you scroll up or look back in your notes, the critical value we are looking at here in this case was 3.682. The value of f that we calculated is larger than the critical value. So we want to reject the null hypothesis and accept the alternative hypothesis. For this distribution, for whatever we're talking about here, for whatever these 3 samples came from, there is evidence of a difference between the means in the samples. It's a lengthy test, it's a lot of calculation, but I think it's interesting to go through and understand where these things are coming from. One of the things I really like about this particular test is that it shows off pretty explicitly where the degrees of freedom numbers are coming from. It's literally, we're dividing it. The degree of freedom in the numerator and the degree of freedom in the denominator are numbers that are used as part of the calculation, in addition to being things we look up on our table. In any event, that's all I have for you on this video, and this is the last video of the course. So thank you for joining me this semester. I hope you found something interesting in this, and maybe I'll see you in another one of my courses.